we are trying to find lower and upper bounds for this competition level problem. And I should write right here for all x, for all real x. This is left out a lot, and I notice on some channels I'll leave it out quite a bit too, but the value, this means for any x, we can find a little m, which is the maximum value, and a big M, which is a little m, which is the minimum value, and a big M, which is the maximum value. And that's partly because the cosine and sine are both trapped between, let me just write, both cosine and sine are trapped between -1 and 1. Let me just write them delimited by commas here. Cosine x and sine x by the unit circle definitions are between -1 and 1 inclusive. You recall sine is just the y coordinate on the unit circle, and cosine is just the x coordinate on the unit circle. Okay, so let's see what we can do here. Now, as you may have surmised, these double angle formulas are going to be fairly useful right here. In particular, you can rewrite this one as sine squared x. Let me write this here, sine squared x equals to, let's see, if we bring it over, what would that be? 1 minus cosine 2x over 2. Right, folks? That's useful to, let me get that written in there, all over 2. Did I do that right? If you bring this to the other side and subtract this and divide by 2, this is what you get. And you see that's pretty useful because we can use this substitution to replace sine squared x right here with something in terms of cosine 2x. Okay, that's the main idea. You see right here, sine squared. And it's a similar sort of argument for this other double identity, a double angle identity. Sine 2x is equal to 2 sine cosine x. The very same thing, it's going to come in handy right here. Okay, and so you can see, I didn't show every last detail, but I said these are the double angle identities, these two guys right here. So using the double angle identities, our expression of interest becomes equal to this. Okay, you guys double check me on that. I'm pretty sure I got it right. Now, so what we get here when we get the 80 and the 41 added, we get this expression. In other words, our original expression that we're trying to find the lower and upper bound for is actually equal to this. But notice that 2x, we can just take this 2x right here to be theta in this other result that I used to know how to prove this. I think I've forgotten. Obviously, it's going to be dealing with the addition formulas of sine. But if we take 2x to equal to theta right here, and y'all, we don't need to know alpha here because you can just tell we're just interested in bounding, but alpha would be equal to arctangent of the quotient b over a, if you need to know that. All right, so again, assigning 2x to theta, we're going to get a bound on this part right here, which is crucial. If we can get a bound on this portion right here, we'll be done. So let me circle this piece right here. This piece right here, according to this range function, and r is literally the range, it's the amplitude, okay? In fact, let me be a little more precise about what this r actually means. What it means is that minus r, take r to be a positive real number, I guess. But r would be less than or equal to a sine theta plus b cosine theta. And I sort of remember the derivation of it. I'm just going to state it as a fact right now, but it's something that a lot of trig teachers, I don't think, teach that much. Okay, but so this is a bound on an object that we have. See? Okay. This this object right here that I've circled is in this form for theta is equal to 2x, right? So we can write down that this piece right here is going to be between, let me put it like this, the bound will be, the bound will be the square root of 30 squared. And I'll go ahead and lose the minus because it gets wiped out anyway, right? I mean, it gets, well, I'll just write it for the sake of completeness. Minus 40 quantity squared. Okay. Now, yeah, that is definitely equal to what? 50? It's equal to 50. So we know that 50 is less than or equal to this, and we know that we know that minus 50 is less than or equal to this, and this object is less than or equal to 50, okay? So what that means is that our expression of interest right here will be less than or equal to, in other words, the bound on this expression, you'll have to subtract 50 from 121 and add 50 to 121. So what we get is minus or plus 71 is less than or equal to the expression we're working on, 81 plus 60 sine x cosine x what do we got here? Plus 80 sine squared x. Okay, is less than 50 plus that number. Okay, so what is that? We got 71 right here, and then it'll be 171. Okay. This number right here is what we're worried about, folks. We subtract 50 from that to get 71, and then we add 50 to that to get 171. So we'll have less than or equal to 171 right here. 171. Okay, so folks, this will be the big M we were looking for. Okay, and this is going to be the little m. Okay, so we've done, and y'all, it's kind of neat. Use Desmos or something to graph this. And you'll see that it's stuck between these two numbers. And you could calculate the angles by doing what I said earlier about alpha. Alpha's arctangent of the quotient b over a, if you want to calculate the period of this thing. But we're only looking for the maximum value and the minimum value. So I got 71 and 171. Okay, so let's come up here and write that in. This would be 71 for little m, and then 171 for big M. And again, this was it's similar to an SMO Senior, 2025, I believe it was problem 6. But anyway, I'll get that circled right up here. And it was a fairly challenging problem in the sense you had to use 3 different identities, I think. That's the only way I knew how to do it. I guess you could use standard calculus on it and check it, but that'd be slightly more tedious in my opinion. But anyway, you may want to give that a whirl. So I think that's about it. Okay. Thanks for viewing.